See, we were discussing about doping and just starting on transport now in semiconductors. And the assignment that's due this week, the first question is primarily on doping, and the rest of it is on transport. And if you have already started working on that, great. If not, I think after the class today, you should be able to answer the entire, everything, including the last question on Schottky diodes. You should be able to answer them. So what I wanted to kind of stress is once we have a good handle over how to put carriers in the bands of semiconductors, and have a couple of core concepts of transport, which is if I know my energy band structure, EK diagram, how do I find the currents that are flowing because when electrons occupy those states in the EK diagram. So once we know that, you can calculate pretty much any transport problem, Schottky diode, nanotube, two-dimensional electron gas, whichever be it. You can calculate it by invoking these concepts. How do the states get occupied? And then once they're occupied, what are the velocities? At what velocity is this state moving? Once we know that, you can sum them all and you get the current. So that's the basic idea. And what we started talking about was doping in the last class. Fortunately, again, I had a few simulations to show, but the lamp is blown, but that's okay. We'll be okay with that. Few major results we derived in the last class was that the electron density in the conduction band, if I'm looking at a band structure of a semiconductor that may look like that, E versus K, energy versus the wave vector. And this edge we labeled as E sub C as the conduction band edge, and the top of the valence band here as E sub V, and the energy difference between the two as the gap, right? The fundamental band gap of the semiconductor. And after quite a few, so essentially we then discussed that starting from the band edge, the density of states will go as square root of energy if it is 3 dimensions. Similarly, there will be a density of states in the valence band. And what we showed was if you kind of make certain approximations, you can kind of bunch these DOS into one band edge sort of density of states, another band edge density of states, with the value being n sub c and the value being n sub v. These are from here to here, we're making some approximations. And once I do that, I can write that the number of electrons in the conduction band is roughly the density of states times an exponential factor that goes as EC minus EF over KT, where EF is the Fermi level in the wherever the Fermi level would be. So if it is here, let's look at if it's here, then EC is at this edge, EC minus EF is a positive number, so e to the power minus this argument is positive. Therefore, the carrier density would be much lower than the NC, right? So that's what we mean, e to the power minus a large positive number. And on the other hand, if EF is very close to EC, you can see that your carrier density will approach this sort of density of states. And this is of the order of 10 to the power 18 or 10 to the power 19, depending upon the semiconductor we are talking about. Okay, so, and similarly, the whole density has a similar formula. I'm not writing them all over again. But again, if the Fermi level is close to the valence band, you have more holes. In other words, this is completely occupied with electrons. And then if you bring the Fermi level close, you start depopulating, and creating more and more empty states. So that's the holes in this semiconductor. Right? And we found that for a semiconductor under equilibrium, NP will be equal to Ni squared this is, again, an approximate relation. You actually have two Fermi-Dirac integrals here. Only when you can make an approximation like this, you can write it as NP is equal to Ni squared. This indicates that for a semiconductor that is completely not doped, if you have completely undoped semiconductor, let me write it this way. That would imply that there's no other source of charge, so any holes any electrons you have in the conduction band must have come from thermal ionization from the valence band. So that's, if it's an undoped semiconductor, then N is equal to P, is equal to Ni. So I think there was a question last time that if you create imbalances, so if you have undoped semiconductor, this is the situation, right? N and P are equal, but if you dope it, then the statistics can change. But for a doped semiconductor at thermal equilibrium, at let's say thermal equilibrium, NP is still equal to Ni squared, and I'll discuss a little bit about that right now. Okay? NP is still equal to Ni squared. This relation doesn't change. But what changes is the nature of the charges. Here you had no dopants, so the negative charges you had were electrons, the positive charges you have were holes. But once you dope it, you can have ionized donors or ionized acceptors. So these are extra charges that hang around in the crystal. And the total charge neutrality relation says that total number of negative charges, which is electrons plus ionized acceptor, the ions of the acceptors that are ionized, is equal to total number of holes plus the number of donors that are ionized. And just to be clear, the donors and acceptors are a donor atom, once it donates an electron to the crystal, the electron that came in with it can move around, but this thing is positively charged now and it's stuck in the crystal, right? So that's the Nd plus we're talking about. It's a positively charged ion that's stuck in the crystal, which is not mobile. You can apply electric field, it's not going to move. But that electron will move, it will respond to electric fields, right? So, and similarly, the ionized acceptors will have a ionized negative charge, an ionized negative charge, and then there'll be, essentially it would have pulled out an electron from the host lattice, and therefore, let's say there was a chemical bond between two sites here. So these were two bonds. It pulls out one of them, and this electron gets stuck here. Therefore, you get a hole, and that hole can now be mobile. It's an empty electron state that can be mobile. So that's from the valence band. And so in other words, if you put a donor, it donates an electron into the conduction band, right? But if you put an acceptor, it pulls out an electron from the valence band, and then it itself gets negatively charged because that electron is stuck there, but it leaves behind a hole, an empty state, right? And both of these are mobile. This electron can move in the conduction band, the hole can move in the valence band, right? So is that here? Now if you dope it, this is your charge neutrality condition, and this is what you always use to find where is your Fermi level, right? And then from here, this depends on Fermi level. The way the donor and acceptor densities depend on Fermi level, there's a slight wrinkle to this. You would say, ordinarily I would say that if I have a donor state, which is positive charge, basically, let's say I have a donor state is a phosphorus in silicon crystal. Let's say all the atoms are silicon except this one, that's phosphorus. That has an extra electron, right? So now, if it donates to the crystal, then obviously it's positively charged now, right? I mean, the electron has left the phosphorus atom, and one electron has left the phosphorus and is positively charged. So you can ask, what is the at equilibrium, at thermal equilibrium, what is the probability of occupation of the donor state? When it has done its job, it is not occupied by an electron, it has lost it. No? Does it make sense? So the probability that the donor has done its job is 1 minus the probability that the electron is still sitting in that state. Right? So when it's sitting in that state, it's neutral. Right? this atom is neutral, and you haven't been able to put an electron in the band yet. So there's no transport. It's not yet n-type doped. So the probability, you may think that so what I'm trying to say is if you have the donor atom, let's say this is your crystal, if it was charged, then obviously if it's a positive charge and there are electrons moving around in the conduction band, then there is a potential well, and the electron will be attracted by Coulomb attraction to the positive charge, right? So there's a well. But I think you can see that if this was not charged, if it was not ionized, then there is no such thing. I mean, this is missing. There is no potential well. Right? So this is kind of a strange situation. What it means is I have a state here which can take on a few forms. Either it can be unoccupied. Let me just outline this, and I'm going to write this in terms of energy. So the donor state, which is that state there, could be unoccupied, in which case the total number of electrons in it is equal to 0. There are no electrons in it. Or it could have one electron. Now, this is you want this. You want it to be unoccupied, meaning you want the electron to be in the conduction band, right? So you want it. But if the electron is not ionized, it could be, the electron could be stuck here in the donor state, inside the potential well. It could be stuck here. Right? It's not able to move around in the crystal. But then there are two possibilities for it. It could be either upspin or it could be downspin. There are two possibilities. So these are distinct possibilities. Now, if I try to put two electrons, obviously this state can hold in principle two electrons, right? But if I put two electrons, you can see that this electron state is very unlike a band state. A band state is a state where the electron is completely delocalized. It's seeing the whole crystal. It's a wave through the whole crystal. But here, this is like an atom. The electron is stuck to the to the donor atom, right, to the phosphorus. It's a positively charged, and so this electron cloud is localized. And so if I want to put another electron in it, there will be, these two electrons are very close to each other in space, in real space. They are not waves. Yet. Does that make sense? As a result, there's a huge amount of Coulomb repulsion. There are two like charges, so there's a huge amount of Coulomb repulsion. Therefore, what happens is if I want to put two electron states, I can't have the same energy as these states. The energy will float up to a certain value, and that's typically called a Hubbard energy, or U. And this is a many particle physics picture. Basically, you can't put two electrons in the same state. And then if you were to put two, then the energy cost would be much higher. That's the meaning of it. So you have four situations: either no electrons, one electron, or two electrons. So there are all these possibilities, and each of them has a certain probability of occurring. This is you can calculate the thermodynamic or the Gibbs probability of each of them occurring. It all just depends on the energy and the Fermi level. That's all it depends on. And I'm not deriving this. It's done in your slides. It's actually a little bit later, around lecture 24. That's where the donor statistics is explained. So please read through. It's a little bit later in the slides. Let me just, lecture number 24, slides corresponding to that. That's where it's described. So you can just have a look at it. But once you do this business, what you get is the total donor acceptor ionized state is equal to the donor density, the chemical density of donors. How many atoms are there in the crystal per unit volume? Maybe 10 to the power 17 per centimeter cube, whichever be it, divided by 1 plus E to the power the donor ionization energy minus the Fermi level over kT. But this would be like a normal Fermi-Dirac distribution, but because of this many particle physics, you get a 2 here. This is very interesting. It's not a Fermi-Dirac distribution. A Fermi-Dirac distribution assumes non-interacting particles, non-interacting particles. But the moment you have many particle physics, you have these sort of strange things come in, and there's a 2. So for this course, it is always 2. So it can take many forms. Depends on possibilities. For example, if you have, so it need not be 2, but here for the semiconductor donor acceptor situation, it is 2. Okay? Yeah.
If you were just really, really, really large, it seems like you wouldn't have to worry about the fact that you can put 2 into that state, and
So-
then back to the non-interacting.
A good point. This is assuming U is much larger than all other scales here, this result. If it was smaller, if the Coulomb attraction was smaller, then the U will appear here too. So, yeah, you are right. I mean, basically, to put two electrons, the energy really floats up, and it's thermodynamically inaccessible at room temperature. You can't access that energy anymore. That means, basically, all it means is you can't put it using heat, using the lattice vibration energy. You can't put it here. But if you include it, it will show up here, is what I'm saying. And depending upon the Coulomb interaction, yeah.
Why exactly is it 2?
So if you find so you can see that unlike a normal Fermi-Dirac distribution, here the occupation probability of this state is actually can be 2. The occupation probability can be 2. It can be 0, it can be 1, or it can be 2, right? So it's somewhere between 0 and 2, not between 0 and 1 anymore. So that's the occupation probability. So what you will get is 1 over 1 plus so your occupation probability will look like 1 plus half times the exponential, and this is saying it is occupied. When it's occupied, the charge is neutral. When the donor is occupied, right, the charge is actually neutral. And then you find the probability that it is not occupied is when you get charge, right? So that's 1 ND times 1 minus this quantity. That's how you get the 2 here. So here half goes to the top and you get a 2. So you can see this probability when this factor is close to 1. So you can get a factor of 2 here, is what kind of thing. So this factor can become very large. E to the power this term can become very large. And this term is much larger than that, so the 2 goes to the numerator, you get kind of a 2. So you can explain this whole thing. I'm not getting into this in too much detail, but this is the donor and acceptor statistics. Both for donors and acceptors, you get a 2 here for our course. So when you solve the problem, use it in this way. So what I've given you in the problem are things like what is the doping density, what is the donor activation energy, what is the acceptor doping density. So essentially, you just kind of solve this now, right? And your only unknown in this equation would be the Fermi level. Right? So that's very fine. And if you write this code, if you solve this problem, you're pretty much solved, and you write a little code for it, that will take care of any semiconductor you may ever encounter. You can just change the band gap, the doping density, activation energy. You will always get the carrier density right away from there. Yeah? So this is essentially, it solves the doping problem completely for semiconductors, this equation, once you solve it. Does that make sense? Yeah. And now that being said, that's a numerical solution. What I wanted to give is a very quick feel of how you can get numbers. Let's say I take silicon and I dope it with ND of 10 to the power 17 per centimeter cube. Now the question I'm going to ask is, what is the electron density in the conduction band? So I dope it with donors, say phosphorus, and I say the activation energy, give or take, 10 millielectron volts. This is a good dopant because what I need at room temperature, basically the kind of dopant I would choose is such that room temperature gives me enough kick that the electron is kicked out into the conduction band. That's what I kind of need. So room temperature is 26 millielectron volts, so 10 MeV, it can take care of that. But it will not be completely ionized. There will still be some, stuck in the donor. So if this is the donor doping density and the activation energy is say 10 millielectron volts, then how many electrons do I have in the conduction band? How many holes do I have in the valence band? This is a question I can ask, right? So maybe you can take a guess. How many electrons will I have in the conduction band, roughly, order of magnitude? You'll have roughly this much, maybe a little less. You can't have all of it because still the activation energy is, finite, but it will be close, right? Now, how many holes will I have? Right, so you just invoke your law of mass action again, NP is equal to Ni squared, right? So you just invoke it, and you get that, then you must know what is Ni, right? And Ni for silicon, Ni depends only on the material parameters, so that's roughly 10 to the power 10 per centimeter cube. That's, we had written down the formula for it, NCNV Eg over 2kT, right? So you can calculate that, and it depends on temperature, obviously, very exponentially sensitively. But at room temperature, that's roughly the number. So here I can say that N is roughly equal to ND. I can say that, and I'm going to prove why now. I'll prove it making it exact rather than being rough. Okay. In which case, because NP is equal to Ni squared, then P is Ni squared over N. Now this is always true. This is always true in thermal equilibrium. Here, it's Ni squared by Nd, right? So, and therefore, good order of magnitude, 10 to the power 20 over 10 to the power 17. So you get 10 to the power 3 per centimeter cube. So that's why you can, for all practical purposes, just forget about the P compared to the N's. This is an N-type semiconductor, even though there are holes. It's not like there are no holes in the band. Yeah.
What does ED represent?
Oh, ED. So this is a donor activation energy, meaning when I put the phosphorus atom or the donor atom in, so the donor atom is kind of it's not a silicon atom in this crystal. It's an atom which has one extra electron. Right? So it's from group 5, for example. Right? So one extra electron means that in these bands are all the electron states of the silicon crystal, assuming that there were silicon atoms everywhere. But now you have one extra electron, so it must have a state somewhere. Right? And we haven't yet accounted for it. A good donor is when that state lies just below the conduction band at that donor activation energy. So the energy from the state of the electron energy here, from the electron, if it was tied to the donor atom to the bottom of the conduction band of the whole crystal, that is the donor activation energy, the energy it takes for you to kick this electron into the crystal physically. Yeah. And typically you want to get that done with temperature, with room temperature heat. So that's why we are choosing. On the other hand, if you want to put in donors for whatever reason and you don't want them to ionize, there are actually cases where you want that too. You want to put in donors, but you don't want them to be ionized at room temperature. You want them to kick in only at say 500 C. Let's say you're drilling, for oil, and there you want the electronics to be, more efficient perhaps at high temperatures. And it is a high temperature electron. Then you kind of want to put it a little deeper, and then, so this is extremely sensitive temperature sensor too. It can sense temperature depending upon how many electrons you have. It's exponentially sensitive to temperature, right? So, okay, so. Now, if on the other hand, I want to be a little more accurate and not say N is roughly equal to ND, let's say I have no acceptor atoms at all in the crystal, then I must solve this equation. I have no acceptor atoms, what am I doing here? Sorry. N roughly equal to ND plus P. That's the equation I should solve if NA, I have not put in any acceptors, right? So, yeah.
Why roughly equal to? Because this is charged.
Actually, you're right. This is exact. It's not rough. Yeah, this is exact. Thanks. So now, let's say I have chosen a donor. I can use this 10 MeV and write it exactly and all that. Let's say I make it even smaller, in which case I'm going to make, say, the ND plus is rough. Now I say that's equal to ND. It's very close, let's say. Then I must solve an equation that looks like this. I'll put this approximate because it's, right? This is a little more accurate now. Right? And what is P? It's always Ni squared by N, right? And you now see you've got a quadratic to solve, and you can solve the quadratic to get how does electron density depend on doping and on Ni, right? And what you'll get from solving this is that N will be roughly equal to doping density. Then you get like it's a quadratic, so you get a square root. What was that? 1 minus 4 Ni squared by Nd squared whole over 2. So that's something you'll get from the quadratic solution. And here, it's kind of a very illustrative example. The negative sign we throw away because we're looking at positive charges here. We're looking we know that at high doping densities, we are going to achieve all of Nd. We're going to release all of Nd. And this shows that if your doping density is much larger than the intrinsic carrier density, right, you can also neglect this term, and you get, this thing just becomes 1. Right? And so you get N is roughly equal to Nd. So you recover all the charge. But if it is not, if you have a very narrow bandgap semiconductor, Ni is very large, because then you may have to be a little careful. In a narrow bandgap semiconductor, it is harder. So you have to be a little more careful with all these statistics we are doing here. If Eg is a few times kT, then you have to be a little careful. I can't make these approximations. Yeah.
Is that quadratic correct? Because it's going to be -4 times some large number, so it would be an imaginary number in there when you take the square root.
You can check this. You're saying is the quadratic? Oh, whoa, wait. Is this minus or plus? Is that what you mean? Sorry.
No, never mind.
Yeah. No, Ni would be much smaller than Nd, but yeah, okay. Check. I think this is correct. Yeah. Okay, so that's another approximation, but you can kind of solve it exactly the same. I mean, but these are very quick and nice approximations. You can give you a feel also of how much should I dope. You should definitely dope much larger than Ni. And Ni for silicon is 10 to the power 10 per centimeter cube. So if you dope only 10 to the power 9, actually it's usually we can't, even today we can't make it that pure. Silicon. So just to be clear, the purity level we're talking about 10 to the power 10 dopants would mean 10 to the power 10 dopant atoms per centimeter cube divided by how many atoms in the crystal, 10 to the power 22, 23, right? Atoms per centimeter cube. So you can see it's, the purity level here is 1 in 10 to the power 13, so it's very, very high. You can, so silicon is close. You can actually measure intrinsic properties in silicon. So it's the purest material ever synthesized on Earth. So, yeah.
So when we say a semiconductor is, let's say, lightly doped versus heavily doped, is that with respect to the intrinsic carrier concentration, or is that just a colloquial for just a range?
So when we say heavily doped, when we say a material is doped or semiconductor is doped, we always mean implicitly it's much larger than Ni. We already implicitly mean that. It's orders of magnitude larger than Ni. So that's what we implicitly mean. Now when we say heavily or lightly doped is when your doping density becomes of the order of the band edge density of states. That's heavily doped. Heavily doped, for example, for 10 to the power 18, 10 to the power 19, that's a heavily doped semiconductor. And the Fermi level is kind of moving into the band now almost. Right? It's very close. Lightly doped would be Fermi level. So intrinsic would be when it's in the middle roughly. Lightly doped is somewhere up here, maybe 10 to the power 17, 10 to the power 16 is a lightly doped. That's kind of a small window typically. I'm talking about silicon or gallium nitride, these materials. This is, that's the parlance. I mean, heavily doped means density of states. Carrier density is roughly 10 to the power 18 to 19 per centimeter cube. And lightly is 10 to the power 15, 10 to the power 16 per centimeter cube. Yeah. Okay, so what I'll do is after the break, I'll come back to the quantum theory of this electron going around the atom, and we'll see it will be basically the model of a hydrogen atom, pretty much. It's sitting in a host crystal, which has a different dielectric constant and all that sort of thing. That's the effective mass theorem. But at this point, I'll just kind of summarize this, and in your problem also. Once you put these electrons in the band, I think you can calculate your conductivity. If I have an n-type semiconductor, Q times n times mu, this is something we did in the beginning of the course, Drude model. If I give you the mobility, and now you know what's the electron density from this sort of picture, right? How many electrons are there in the band? I can calculate the conductivity of the material, right? And if I have holes as well, so you can have n-type conductivity, also p-type conductivity. You can have both. There are some materials where you can have both when the bands overlap and that sort of thing. So you can have this. And I think in one material, that these are related at thermodynamic equilibrium. So that's something I've asked you to just play around with it and prove that there's a minimum conductivity. And you can't get lower than that conductivity. It's kind of an interesting problem. Yeah. Okay, so now any questions on this? And just to be clear, also a very important property of, or rather experimentally, we can make a lot of semiconductors. A very good example is diamond. Diamond, so it actually almost does not matter how large is the band gap. Sometimes you read a textbook, solid state physics, you say, oh, 5 eV band gap, it's an insulator. Not necessarily. Any material that has a gap that you can dope, if you can put electrons in the conduction band or holes in the valence band, if you can dope a material, an insulator, then it's a semiconductor, and that's pretty much it. I mean, if you can dope it and populate the bands and make it conducting, you can get conductivity in the material controllably, then it becomes a semiconductor. So diamond has a gap of 5.8 eV or so, and currently people can only dope it p-type, but no n-type. Gallium nitride, big success story, one of the biggest revolutionary semiconductors since silicon. For about, people knew it was a semiconductor since in the 1950s, but it's just that people could dope it n-type very nicely, but nobody could figure out how to dope it p-type. And finally, this group discovered, and then it completely, once you can dope it n and p, you can make LEDs, lasers, transistors, all that sort of business. So it kind of unleashed that property of this wide bandgap semiconductor. So you're in your assignment problem, you are solving this sort of, saying that this is a deep acceptor and all that, you're solving this problem. So doping is actually, it is what determines whether a semiconductor makes it, or it is, kind of, for applications, or it actually remains as a, we have not been able to harness its full potential in some sense. So yeah. Okay. Yeah.
So if the activation energy is on the order of kT, can we just assume all of the atoms are ionized?
You can, if you are doing an analysis like this, or if you are designing some devices, I would say yes, absolutely, go ahead and make that assumption. But if you're solving a problem where you have to be very precise for, like an assignment problem, then you can definitely use that first to get a quick estimate, and then solve it exactly and say my estimate was correct or something like that. That would be best. Yeah.
What about on an exam where you're short
Oh,
on time?
if you're short on time, just use your intuition and say that yes, I'm going to assume it's ionized. That shows, that counts a lot if you can, make such assumptions based on your intuition. So yeah, all right.
Will this material be on our exam?
Doping? Oh, absolutely. Yeah. We will. Yeah. Okay. So now I'm going to step slightly away from the doping problem. We'll come back to it because we'll see that this chemical doping is obviously not the only way of doping it. In a transistor, we are effectively populating bands by field effect, and later on we'll see by light. You can put carriers in the bands in many, many ways. And each of them is a very important application of this of semiconductors. So what I want to do now is say that if I have managed to put carriers in the bands, so I put carriers in the band, and now I want to ask the transport problem. Or look at the transport problem and say that now I'm going to connect electrodes to it and apply a voltage, how much current is going to flow? So that's the question we're going to ask now. And so the way I'm going to approach this problem is somewhat different from what traditional courses would do. Traditionally you would approach it from a semi-classical perspective, where you start with the Drude model, say there's scattering, there's, they get mobility and velocity saturation and all that sort of thing. We're going to come at it from completely opposite perspective. Because we have invested so much time looking at the full quantum mechanical treatment of a crystal, we're going to first start with a completely quantum version of transport. So we're going to solve the quantum transport problem for any semiconductor, and metal as well. Not necessarily limited to semiconductors. So here's the question. We have EK diagram, and let me I had a few simulations for this, but that's okay. We can see those pictures in the next class when the video is back up. So I have this EK band structure. Right. And by some means I have put electrons in the bands here. Say I populated that state. Could be by doping, could be by some means. Okay, so here's an allowed state for electrons. Say wave vector k, and I have put an electron there, right? By whatever means. And now I want to ask this very simple question: that what is the current carried by that state k? Right? What is the quantum mechanical current carried by that state k? That's the question I want to ask. Because if I can answer this question, what is the current carried by this state, I can just sum over all states that are occupied and get the total current. Right? That's done. So any quantum transport problem, that is exactly what you're doing. you're finding the state K, finding the current carried by that state, and then just summing it over all. Yeah.
Would that be little j?
Okay, so we can start with little j. That's so little j would be the current flux, and and then if you want the charge current, you multiply by the electron charge. Yeah, we can start with little j. That's so little j would be the what you call as the convection or the flux that particle carries with it as it moves. And now, if you want heat current, you can multiply it by its energy Ek. If you want the charge current, you multiply by Q, and so on. So, okay. So let's look at the more fundamental flux current density. Now, before we, let's kind of recalibrate ourselves. We have already done this problem. We have already solved this problem, but only for the free electron. Right? We have solved this problem. You did the, for the free electron, we knew its wave function, right? Psi k of x. If it's in one dimension, it's just 1 over square root of L e to the power I kx, right? We knew that. Then we went in and said that, well, I know the formula for jk, and that just happens to be minus I h bar over twice mass of the electron, psi star d by dx of psi minus psi d by dx of psi star, right? I mean, we had kind of derived all this stuff in the beginning of the course, and you applied it to many problems already, right? So if you know the wave function of a quantum state, I can immediately give you what's the current of that state, right? Because this formula gives you that, right? Now what has changed now? So what has changed is this state is in a crystal. It's not a free electron anymore, right? What is the wave function of this state now? Right, it's a Bloch function now, right? The Bloch function looks very similar to this, but the slight difference, right? Slight difference. What is the difference? It is modulated with the periodic crystal lattice, right? That's a plane wave with x, right? Now, because the atom, because of the thing is in a lattice now, and the lattice has a periodic potential, let's say something like that, right? The Bloch function now looks like a big jump here. So essentially, it's the plane wave, but it's still it's modulated by a. Does that make sense? That's what it is. It's modulated by that, right? If you remove the crystal, if you remove the lattice, this becomes 1, and you recover your free electron. So you drew the free electron band structure too, right? You drew the free electron band structure, and the free electron band structure looks like this. We already solved that too, right? And this is where the gaps and all came from, right? This is free electron band structure. That's another free electron band structure. And only when you put the crystal in the way and you turn on the potential, the band split and you form this band, right? This is where it came from in the beginning, right? So let's see. So what does that mean? The discussion we're having is, here's the quantum wave function or the state of the particle in a crystal, right? And I want to find the current due to that state, and I know that that state is very close to this one. It came from here, but it's not composed of only this state. It's composed of a little bit of that, a little bit of something over there. It's mixed up now, right? Because that electron, classically, if you think about it, is going along, if there's no lattice, and it would have this energy, it would have that wave function, just that, right? But now, because you put the lattice in it, it gets kicked around with a momentum of plus g or k minus g, so it gets kicked around because of these particular momenta, right? So there's a little bit of mixed state. So essentially, this state, I can write it as c k times k. This is a free electron state. If I had only a free electron, this would be the energy state, right? I'm just kind of qualitatively writing it at this point. Plus c k minus g of free electron, plus c k plus g, k plus g. It's essentially, at least plus quite a few others, right? Plus 2g, minus 2g, and all that, right? So these are just coefficients, right? And what I'm saying is this state, this quantum mechanical state, is mostly from this band, but there's a little bit of something else, right? So it has all these different components in it. So the question I may ask is, so can I, if it was a completely free electron, it's very clear what is its velocity. Velocity is h bar k over the mass of the electron, free electron. There's no doubt about that, right? Right, because the energy is just h square k square by twice the mass of the electron, then the velocity is just that. This is kind of classical picture. I mean, this is when quantum and classical become equal. It's momentum by mass is the velocity, right? So, but now you can see that if I were to kind of find the velocity of this electron in the Bloch state, then it has a little bit of this k, it has a little bit of that k, and so on. Right? It's a mixed state now, right? So the velocity would look something like this. This is not, but I hope you can see what I'm trying to say. Velocity will have this much probability of being this velocity, plus ck minus g squared. This is the amplitude square is probability times k minus g over mass of electron, right? Plus, and so on. Does that make sense what I'm doing here? Over mass of electron, and so on, right? So it's a mixture of many waves with slightly different velocities. Right? There's a peak one which is centered around here, but then there's a little bit here, a little bit. So as a result, the mean average is this whole thing divided by all your sum of ck's, which is actually 1. So that's your, and then this velocity is termed as the group velocity. It's called the group velocity. That's where the name comes from, because it's composed of many different, velocity components. And so if I find that, then I am. Actually, the current happens to be just the group velocity divided by the length of length of the volume. So it's exactly equal to that. It's the mean value of here. Okay? But we are going to do it proper. I mean, we're not going to make any approximations like this. We're going to do it exactly now. Now, before I go, just want to pause for a moment and say that this is a very interesting situation too. Let me, basically write the expression down, because it's going to be no surprise at all that the Bloch function, no matter how complicated your Bloch function is, once you know your EK diagram, this EK diagram, then the quantum current is given by 1 over h bar, d by dk of the energy. This is an extremely powerful and almost remarkable theorem. It takes a little work to prove it, but it's fine. So this is the expression for the current carried by any state, Bloch state k. And so what it's saying is, and then to find the total current, typically you integrate over space, so this will become just 1. This will just become 1 psi squared. And so this is effectively now, this is your group velocity. And in 3 dimensions, it's a vector, and instead of a d by dk, you have a gradient in the k space. And you've already kind of started doing problems with this. But so what I'm trying to claim now is the same expression we have talked about earlier. Or rather, the quantum current carried by a Bloch state is given by the group velocity of that state. And this is, I would say that a very remarkable, very powerful theorem, and we're going to apply it many times now. Okay, but first let's derive it. Right? But before I derive it, one more thing I wanted to say here is, you see, it's kind of a very strange situation now. So if I put a state in, if I populate this with an electron, if I put a electron in that state, say upspin, right? Then what quantum mechanics is telling me is that that electron will have a certain group velocity, right? It's given by the slope here, the slope. And that electron, if I have a physical crystal, right? Let's say a physical crystal, and that k was pointing maybe in this direction. So that what it's saying is, if I put it in this state, remember this electron state has come from solving the entire problem. You have periodic crystal, you have potential, all that stuff. And after all that, you say what Schrodinger equation gave you as, this is my eigenvalue. This is the eigenvalue of a Schrodinger equation. What does that mean? It means it's a stationary state. If I put an electron in that state, it's going to stay there forever. Right? It's not going to dephase on all that, unless in reality there are lattice vibrations, which is another parameter that then you need to add to Schrodinger equation, or electromagnetic radiation, all that. But if you do not allow any of that, if you don't allow lattice vibration, if you don't allow, it will stay in that state forever. And what does that mean physically? If the electron was going that way, it will continue to go in that way forever. There's no stopping it at all. So similarly, there's another state here, and that thing is going like that forever, right? Physically in real space. Right? So you have all these electrons going in various directions in K space, and they're going forever, obviously till they hit a surface or till they hit a junction or something like that, and they can jump over. That's a Schottky diode if you jump over a barrier and all that. So this motion, this sort of motion would be called a ballistic motion. It will keep going forever. There's no impeding it at all. Right? So in the classical theories, Drude model, the question there was, what is the origin of why are the idea there was the origin of resistivity was electron was bumping against crystals, and it was bumping against the atoms of the crystal and lattice, and that's why you had resistance. Here the problem is turned completely upside down. Here what we're saying is, if the crystal is perfect, you cannot have any scattering. You cannot have any resistance if you have a perfect crystal. The origin of so meaning if I have a periodic arrangement of atoms, in principle, when you have ballistic transport through it, you will have infinite conductance. We are not talking about superconductivity at all right now. It just says infinite. The origin of resistance is if you have any deviations from periodicity. I put a donor atom which is different from others. Any deviation from periodicity is what is the origin of resistance. So that's kind of, it's upside down picture. The quantum picture is kind of opposite, exact opposite of the classical picture here.
Well, what if you're doping periodically?
If you dope periodically, then you don't form, it will not scatter. And it's a very interesting question, point. It will not scatter if you dope it periodically. It also forms a band. The dopants also form a mini band, and right. So it will not scatter. So anything that is periodic, a potential that's periodic, you have to absorb it though in the band structure now. So it will tweak your Bloch function slightly. It will change it a little bit, but it will not scatter the electrons. Yeah.
Is it physically possible to dope something periodically like that?
People are trying very hard, and it's difficult. It is difficult to dope it periodically, but there are ways to do that. Basically, with the ion implant through a periodic grating, and it's possible, but it's very hard. So yeah. Okay. So so this is also. This is a very, I don't know what is the, how true this is, but people had asked Niels Bohr that, so at that time, 1910 to 1950, the biggest unsolved problem in solid state was superconductivity. Nobody had a theory for it, right? And so people had asked Niels Bohr that, are you working on superconductivity? Doesn't it excite you? And he says, yes, I understand, but what really bothers me more is what is the origin of resistance in metals. It's not that, he said, superconductivity to me is a natural state, because of this picture. It shouldn't have any resistance. So what is the origin of resistance is kind of a harder question for him. And it turns out the ballistic theory of quantum transport is much simpler than when you want to explain resistance, which is the Boltzmann transport where you introduce scattering. That gets a little complicated. So the ballistic picture is much simpler, and that's why we're doing it first now. Okay. So, so let's derive this. This needs a little bit of work, and unfortunately, it's not done in most books. It's done in the notes, but in a slightly different way. It's done in this way. But I'm going to just let me just say that you can plug this in here and run with it, but it needs quite a bit of work. So, but let me just show you the outline of how one proves that the group or the quantum current of Bloch states, small j of a state k is given by 1 over h bar. I'm going to just do it in one dimension. It's trivial to generalize to higher dimensions. Okay, so times I'm going to just write it this way, small size square. So to do that, we kind of go to the Schrodinger equation and say that I have solved the Schrodinger equation and found my Bloch states, which are there in a periodic potential V. I'm not going to write as a function of x. It's understood is equal to E of k times psi of k. Right? That's your Schrodinger equation, and the V here captures all the silicon atoms and the potential that is sitting in the way of the electron, right? So, or whatever semiconductor or metal. Ek is uniquely determined, or rather not uniquely determined. So if you know the k, we are assuming we now know Ek. We have completely solved a band structure problem, which you have done in some of your assignment problems, okay? Right? And as you change k, this changes, and the psi changes, right? As you change k, move over the band structure. So what we are going to do here is write it slightly differently, and 2m over h square v minus e of k times psi k. And then kind of looking at the answer a little bit, I'm going to cheat and take a derivative with respect to k. Take this derivative of the Schrodinger equation with respect to the wave vector k. Right? So d2 over dx squared, d by dk doesn't interfere with x, it goes straight in and takes psi k over dk is equal to 2m over h squared. And I'm taking a derivative with k, so you see there are two possibilities, either this or that. Both of them depend on k. So I first take this one, get minus de of k over dk minus that times psi k plus d over dk. Okay, so that's it. Okay, so now what is d over dk of psi? Let's look at this one. We are taking with respect to k, not x, so I'll get what? I times x come out in the front. So I get I times x, but then it will leave the rest of the wave function as it is, so you get psi k, right? Plus ikx times du over dk. So that's the du over dk. So I take this thing and I plop it in here and here, right? Where is that? There, right? So throw those in there, and what I get now is so the reason I'm going through this is it's typically not done in most books, and the second thing is any of you who are interested in pursuing some of the crazier materials that came from semiconductors, like topological insulators and such, this is the route. This is one of the routes one has to take to get there. So anyway, so this one, v minus e of k, I x. All right. Okay. So it looks like a mess, but I think we'll see now. There'll be very interesting, cancellations and all that, and this will pop out soon, but not yet. So what we'll do now is you have the derivatives of this thing here. So let's take that.
Did you drop a h bar squared?
Oh, sorry, you're right. H bar squared. Yeah. Right. So I have a double derivative of ix times psi. So let's take the first derivative. When I take a first derivative with respect to x, I just get x times psi k. So I get I psi k plus ix d psi k over dx, right? And then I take the second derivative, I get psi k is actually e to the power I kx u kx, right? So now if I take the second derivative, you can see again I'll get what am I doing here? Just a sec. I psi k plus, yeah, this question.
Did you also drop e to the ikx d psi over dk, the very last term?
Oh, you're right. No, you're right. So ikx du k over dx dk. Correct. Yeah. So thanks. Yeah. Okay, so so I'm taking this derivative, first derivative with that, second with that.
What about the E?
No, I'm just taking this now because this will we hold on that. Yeah, so that's correct, right? Yeah.
I don't know where you.
Oh, so I'm just looking at this term now, and taking two derivatives, and actually I don't want to take the second derivative. Yeah. I times d psi by dx plus I times d psi over dx plus I x d2 psi dx square. This is a bit of, right. This is what you'll get. In fact, 2. And the reason we're doing this is, you see, I really am after this term. So d psi by dx, and I'm going to get this from here. And it will relate to the group velocity in a couple of steps now. So, right. And then you can take its complex conjugate, all that business. So at this point, what I want to do is rewrite it slightly as 2i I'm going to take everything else to the right side, keep this on the left, and this term I'm going to keep here. H bar squared dE over dk. All right. So this term times psi k, the wave function. Okay, now plus. So there'll be a few terms on the right side now. I'm going to just move them around to the right. So you see there is a I x d2 psi by dx squared. And
Two or I.
this is 2 times I. Sorry. Yeah.
Okay, next to the M on the other side. Is that an I or?
2. This is a 2. All right, 2. All right. So 2m over h squared. Right. Right. So you see, there's a e to the power I kx du by dk, and there's a e to the power I kx du by dk. We're going to group them. It's on the right side of here. It is v minus e, just a multiplicative constant. On the other hand, though, it's d by dx here. So I'm going to just rewrite it now as sorry, e I kx du by dk. Right. So that's one term. Okay, and then I get another term, which is 2m by h squared. So I'm now going to take this term to the right, and now I'm looking at this term here, the linear term in psi k. So what I'll see is there's a constant ix in front of both of them, ix and ix. Yeah. And then inside it, it looks very similar, dx squared plus v minus e of k psi of k. Okay, so I can see there's a good reason why this is not done in books, but all right. All right, so maybe some of you can tell me, what is this? Yeah, so basically what you have here is, this is your, sorry, I think I screwed up again, that's why, sorry, h squared by 2m. There should be a h squared by 2m, because I brought it over from right side, so it's inside the brackets, so okay, yeah, that's the correct version. So, when you notice this term, you see that that's actually a Hamiltonian, the periodic Hamiltonian of the crystal, right? And that thing is acting on Bloch state on the right side. So what will that give you? It will give you the eigenvalue of that state. So you get ek minus ek, that's 0, right? So it takes away this term completely, right? You get a 0. But the one on the top is not 0, because this is not a Bloch eigenstate, right? It has like a derivative with k and all these other things, right? So what you do now is you multiply on both sides by psi k, which is the, so first of all, is this clear? So this goes away because it's just the Bloch state. So I erase it. And now what we're left with here is this term, and what I'm going to do now, you can see also the reason, so I will multiply with psi k star on both sides. There's a I shouldn't forget that. Multiply with psi k star on both sides. And here it's, I don't need to bother to keep it on the left side because it's just a number. But here there's a derivative and operator, so I must put it on the left side, not on the right side. Right? This is on the left. Yeah. And right away, also again, you can see why I'm after this term, because where is my current? Where is my, yeah. All right, so that term. Right? So that's what we're after here, right? So when I multiply it here, now you notice that this, again, is your Hamiltonian operator, right? And this 2m over h bar square and all that are constants, so you can take it out here. But now you can see this operator can act on the left side here. And there is a Hamiltonian operator, or you can take an integral if you're not comfortable with it. And this indeed is an eigenstate of that too, right? With the same eigenvalue, E of k. Does it make sense? Psi star and psi have the same eigenvalue, right? E of k. Right, okay, so as a result, this goes away too. Right. Does that make sense? Once I multiply by psi star and I integrate, it takes away that one as well, because what I'm trying to say is this is Hamiltonian minus the eigenvalue, right? This thing is the Hamiltonian, and it's acting on the left side on psi star of x at k, which is also an eigenvalue with the same eigenfunction with the same eigenvalue. So it just takes. So when it acts on this, it goes zero. So the way to really look at it is you can integrate it and over space, and then you will realize that Hamiltonian can act on the left or on the right. Okay, so with that I get rid of this as well, and I have something nice, which is this expression. I can now come back and take a complex conjugate of it. I get psi k d psi k star over dx is equal to, the right hand side doesn't change when I take a complex conjugate. Psi k, you can write it psi k star psi k, right? And now you can plop them in here into your expression for the quantum current. Where is it? Here. So you get kind of psi star this minus psi star, right? And you can take your 2I to the denominator on this side, by I, 2I denominator here with the I, right? And you take this minus this, right? So quantum current is minus I h bar over twice mass times that thing minus this thing, right? And that you can see they're exactly equal on the right side. Exactly equal but opposite signs, so you get twice. So you get 2m over I h bar squared, and then you get mod psi, right? And so the 2 and 2 go away, I and minus 1. Mass, that's actually mass of electrons go away, 1h goes away. So yeah, you get, right. So this is true for all cases of Bloch electrons, except for one situation. When you apply a magnetic field, it looks slightly different. But for all other cases, and for the rest of this course, this will be expression we'll use for calculating the current due to any Bloch state. You can see it enormously simplifies your life, because once you know the band structure, all you need to do is take a derivative. That's it. There's nothing else really much to do after that. You can find the current of that state. Okay, so the derivation, I think I'll write it up and post it, because this part of derivation, there's Professor Rauner's notes. He has done it this way, which is also kind of a very intuitive way of doing getting to this result. And here this is an exact way of doing it. So, okay, so let's
I think, is there something with a negative sign? If it's negative I and then 1 over I, wouldn't that give you a negative?
Say it again, the minus I over I, right?
Yeah.
You're right. What did I do here? I mean, first of all, this is correct. I think I might have switched around some signs here probably. M over I. Psi star minus I.
In the bottom one, it shouldn't be negative.
It shouldn't be.
The
Okay.
the psi k, d psi k star, d, that should be positive.
That should be positive.
The top one is negative.
Okay, good enough. That's right. Okay. So, thanks. Okay, so I think what I want to do now is kind of use it in one or two cases and use this result to find currents now. So it's painful to get here, but using it is very easy. So we're going to just make use of it and calculate two cases. The first case we'll calculate is I've asked you in your assignment to show that you get for one-dimensional transport, you get a quantum of conductance, which is determined by Planck's constant and electron charge, a fundamental unit of conductance. And I want to kind of set you off on that path first, and that should also tell you how to solve pretty much all other problems in this assignment or any other quantum transport problem. And it should be, it's the basic idea is the same. So let's imagine now that I have a semiconductor with a band gap, and it has a conduction band, right, EK. And let's just look at the conduction band situation. So what I've done is I want to put carriers into the conduction band. So I can dope it. Valence band is full. I can dope the semiconductor, or I could, here's the band gap, or I could somehow connect to the states in the conduction band through a metal. This is called the contact. So what I could do is bring a metal in close proximity and physical, that forms a chemical bond. The metal has no gap. So what I'm drawing here is energy and space. This is space now, not K, but space. Inside here, I've plotted a little EK diagram just for analysis a little. So what I'm looking at now is a metal to semiconductor junction. Okay? And physically, what I've sketched here, you can think of it in the density of states. Maybe the metal DOS is kind of here, and the density of states of the metal is going like that, and you have filled up all the electrons in the metal till here. That's what I'm plotting here. And the semiconductor, similar picture. The density of states of the semiconductor, you have valence band completely filled, conduction band mostly empty, right? But there's a gap in between them. Does that make sense? So this is all concepts we have covered till now: filled band of the semiconductor, empty band, and all that. Right? And now I put the exact same metal on the right side, and I've somehow chosen, amazingly, the metal that the Fermi level of the metal lines up exactly with the conduction band of the semiconductor. I've chosen that. It may not be possible physically, and one of the things you're doing is what happens if it's mismatched, in which case you form a Schottky barrier. So that's solving that. But let's look at the situation where you have ohmic contact. This is called an ohmic contact, when there is no barrier for flow of electrons from metal into a semiconductor. That's an ohmic contact. There are no potential barriers. This is the energy that the electron would see if you were to kind of go this way. Right? Okay, so is that clear what I did here? So I'm just plotting the energy in the vertical direction, space in this direction. Here's the semiconductor, maybe a certain length. It has a gap in the energy spectrum. And then you have the conduction band and valence band. So first of all, just by looking at this picture, valence band is completely full. So even though it has a lot of electrons, it's not going to give you any current. It's completely full, right? Whereas conduction band is mostly empty the way I've drawn it here. Maybe I've doped it and put some electrons here. It doesn't matter at this point. Okay? And now it is an open channel. So there are many energies here. They're all allowed, right? And the metal could inject into those states, and the electrons could go. Okay? So that's the way to look at this problem. And the question we are asking at this point is, I take these two metal electrodes and connect them to a battery with a voltage V. externally, a voltage V externally. So physical realization, I can take a nanotube or a nanowire, and then put a metal electrode here, a metal blob here, and then connect it to a voltage supply. So that's the physical realization of this problem. And this thing is a semiconductor, and that's a metal. And the question is, if I apply a voltage V, what is the current I? So that's obviously the most basic transport problem. If I apply a voltage V, what is the current, right? So we're talking about the charge current at this point. And so the way to look at it now is the moment I apply a voltage V, what it does is the following. So in the metal on the left side, you have a Fermi-Dirac distribution, and the Fermi-Dirac distribution goes through the Fermi level. This is the Fermi level of the metal, and it goes to 1. So way below the Fermi level, the occupation probability is 1, and way above it, it's 0, right? The occupation probability of electrons in the metal, occupation probability of electrons on the right side metal, exactly the same when you don't apply a voltage, right? 0 to 1. This is the Fermi-Dirac occupation function, right? The moment I apply a voltage, what I'm doing is, let's say I hold it where it is, I'm pulling this down by a voltage V. That's what really I'm doing. So when I apply a voltage to anything, I'm pulling the chemical potential or the electrochemical potential at the Fermi level on the right side down by exactly the amount Q times V. That's the meaning of it. So the battery, what it's doing is it's pulling electrons away from here. How did the Fermi level come down? Because I pulled out electrons from here, right? It's pulling the electrons out from here, and it's pushing them. Everything is charge neutral. The battery is charge neutral. This whole thing is everything charge neutral. So if it pulls out electrons from here, it must inject them back in here, right? And that's the reason electrons are flowing this way and the current is going this way. I mean, that's the physical reason of all that stuff that's happening inside there, right? Is that clear? So I mean, when I apply a voltage, I lower the Fermi level by exactly the voltage I apply, and that means I pulled out a lot of electrons, but then the electrons I pulled out, I have to inject it back in here to maintain charge continuity and neutrality, and that's the reason for current flow here. And the reason really is so once I pull it down, the band is going to bend. The energy band is going to start bending because we are assuming this is locked, meaning it's not going to so it's going to pull down the bands with it on this side. And so and in a ballistic situation, all the electrons that are going to the right in this material, that any extra electron that may have come along that are going to the right in this semiconductor, were injected from the left electrode. Meaning the Ks that are positive, these are positive Ks. So essentially, the group velocity here is positive, so the electron is going to the right physically, right? d by dk is positive, so it's going to the right. These states are going to the left, right? Where would those states come from? From this contact. Right? Does it make sense? Right? And I'm completely ruling out any scattering. So if I have a state here, it can't go here. This is ballistic transport. If I put it in any state, it's going to stay there. It's not going to move out of that state till it obviously escapes from the some other end. But physically, what I'm doing now is this is kind of the other important concept to make sure we understand. So I have electron states here. Each of them, I know what is the J of k. We already calculated that. 1 over h bar d by dk. Right, times small psi k square. But this state can be occupied by the electrodes, the contacts that are going to inject carriers or pull out carriers from them. That's how they're going to be occupied. And what I'm trying to say is, if I have such a situation where I have two ohmic contacts, I have a left electrode and a right electrode, then the right-going carriers in this 1D quantum wire or whatever are all in equilibrium. This is an important concept. All these carriers have a Fermi function that, have a occupation function that looks like this: 1 plus e to the power ef of the left electrode. Sorry, e minus ef of the left electrode over kt. This is kind of a. All right. So all right-going carriers are in thermal equilibrium with the left electrode. What does that mean? It means they share the same Fermi level. Same Fermi level. Similarly, all left-going carriers here, these states have an occupation function. So I can write it as F right-going carriers, and F left-going carriers will have an occupation function of the right electrode, E minus right electrode over KT. Does that make sense? I mean, essentially, it's kind of filling up these states. This electrode is able to fill only the right-going states, whereas this electrode is only going to fill the left-going states. And obviously, now there's a misbalance. You are not balanced once you have a voltage in between the two, right? You have more states now going to the right than to the left because, of this function. And here, the Fermi level of left minus Fermi level of the right is equal to Q times the voltage you apply. It's the difference of the chemical potentials of the two metals. So now, given that, physically, if I take it to 0 Kelvin, you can see right away that maybe I have somehow occupied these states, and I've occupied these states, and these states. At 0 Kelvin, Fermi level is very sharp. Maybe my Fermi level of the left electrode is here. Oh, sorry, right electrode is here. Fermi level of left electrode is there, maybe. Okay. And then you can see now the current will be carried completely by, you can just find all the currents and sum them, right, over these states. Or you can see that this part I can neglect because they're balanced exactly. I can just sum from here to there. Right? And when I sum that, so J of K is, well, we already wrote that. So essentially my current will be a sum over K states times occupation function times the velocity of state K. And velocity we already found was 1 over h bar dE by dk times f of k. And the sum I can convert into an integral if I'm doing, if I'm doing 1D transport. So sorry, I should have a 1 over L. If I'm doing 1 over 1D transport, this is my expression. I need to go from k, sorry, just this k to that k. K, I can write it as KL to KR. And when you do that, this kind of 1D is very interesting because everything cancels out, and what you'll get is Q square over H times V. The current will be given by this for one dimension, and this is very interesting. Current is conductance times the voltage, and this depends only on electron charge square over Planck's constant and nothing else. So this is the quantized conductance or quantum of conductance. So for ballistic transport, completely neglecting spin degeneracy, valley degeneracy, and all that stuff, but I think you guys know what to do when you have spin degeneracy, valley degeneracy. They just appear here. Every valley, every spin is a parallel channel and just increases conductance accordingly. So if I have a spin of 2, it's just 2, a value of, just multiply it. Carbon nanotubes, for example, will be 2 and 2, 2 valleys and 2 spins, so it will be a 4. So in carbon nanotubes, you will see 4 Q squared by H is the quantized conductance. And so on. So, okay. So I think we are over time today, but this is an application of the quantum transport, and in the next 2 classes, on Thursday, we will look at quite a few other situations and look at it in more detail. But yeah. So was there a question? All right, we can end here. Yeah.